In this presentation, I will use a relatively simple deep learning neural network to achieve more than 99% accuracy. Artificial intelligence and machine learning has three key components: data governance and pre-processing, feature engineering, and modeling. This presentation will focus on feature engineering and modeling. Here I'm separating the orange and blue dots linearly by using a linear activation function, a learning rate of 0.1, which is default, and with no custom features, and you quickly get a reasonable result. Here the orange and blue dots appear to have a circular boundary, so we're going to use the TANH activation function. The linear activation function here won't work. The learning rate is still 0.1, and if you're adding custom features, then we can add x1 squared and x2 squared as the custom features. I'm in TensorFlow Playground, and the goal here is to separate the or classify the blue dots and the orange dots properly. If I run a neural network, no matter how many iterations I run and try to classify with no hidden layers, it doesn't seem to classify properly or accurately. And then if I run a hidden layer with two neurons, classification still doesn't work very well. But if I increase the hidden layer to include three neurons, classification works much better. There's a triangular shape demarcation point, a demarcation there. And if I were to increase the number of neurons to 4, then there's still a triangular shaped boundary there. It doesn't seem to be any better than 3 neurons in the hidden layer. So now I'm going to add features x1 squared and x2 squared and then run it. And as you can see, there's a circular boundary separating the blue dots from the orange dot, which is the best classification. And then if I remove the hidden layer and the features x1 and x2, leaving x1 squared and x2 squared, it still works perfectly well. Thank you. So what happens when you're trying to recognize handwritten digits? As you can see, unlike the previous demos, it's not easy to recognize features. So we're going to use another interesting technique. We're going to let the computer figure out the features and then do the modeling. So the test environment, so I used the MNIST dataset. The training dataset size was 60,000 records of labeled data, and the testing data size was 10,000 records of labeled data. From a software point of view, I ran this on an Ubuntu machine, created a Python virtual environment. It has the NVIDIA drivers, and using TensorFlow and Keras. The hardware is an Intel i7 chip, and the real thing that really gave me a lot of computing power was the NVIDIA GTX 1070 card, and it's got 16 gigabits of RAM on it. The multi-layer perceptron has the following architecture. Basically, the 28 by 28 images of handwritten digits are flattened into a 784 bit input layer, and next to that is a dense 512 neurons that are ReLU activated and have a dropout rate of 0.2, and then another hidden layer which has 512 neurons ReLU activated with a dropout rate of 0.2 again, and then softmax for the classification, and that's essentially the high-level architecture for the multi-layer perceptron. I have created a simple multi-layer perceptron in Python using Keras and TensorFlow. It has two hidden layers, 512 neurons in each layer, and dropout rate is 20% or zero point 0.2. So it'll run through this process, and at the end of it, it'll go through 20 epochs, and it comes up with roughly 98.4% accuracy, which is pretty good. So the neural network architecture is somewhat different from the multi-layer perceptron. It doesn't flatten it right away. It keeps it as 28 by 28, so that's a two-dimensional matrix. And what we do is we apply 3 by 3 filters, 32 random filters that are applied. And you take that output, and then what I'm seeing is what I'm doing is essentially applying 5 by 5 filters, 64 random 5 by 5 filters. Both these are ReLU activated. And the logical thinking behind that is I'm going to do one set to recognize the features and a second set of convolutions to figure out how the features come together to form a handwritten digit. The next layer is a pooling layer, which really, makes makes it a smaller matrix that needs to be managed. And then the flattening happens after the pooling layer, where there's a 1024 neurons that are ReLU activated with a higher dropout rate of 0.5, and another 1024 neurons that are ReLU activated with a dropout rate of 0.5. And finally, the softmax layer to classify the digits properly. This is a convolutional neural network demo. Essentially, we're running wrote this program in Python, and it's running using Keras and TensorFlow. The architecture here is it has two convolution layers, and each of them are ReLU activated. In addition to that, there's a pooling layer after that, and then two regular hidden layers. But the hidden layers have 50% drop-off rate and 1024 neurons. The interesting thing about this is also I tried dropout right after at the convolution layer. And at the pooling layer, I was able to get better results by using drop-off just at the fully connected and regular hidden layers. And as this program runs, you can see that it starts overfitting at epoch 6, but I ran this before, and as it goes through the algorithms and iterations, it actually provides the best results around epoch 14 or 15. And the accuracy that you get from this relatively simple neural network is about 99.3%. So that's 0.7%, which is pretty good. And compared to the one without convolutional neural networks, just straightforward hidden layers, you know, it's actually a significant improvement. I got 98.4% accuracy there. So the error rate has gone down significantly. It has gone down by more than half. So yeah, so this significant improvement, and on my desktop it was able to run at within 2 minutes. Thank you. Why is this amazing? Well, it's hard to teach kids to recognize handwritten digits. They're not going to learn it in 2 minutes. And even if you take adults and try to uh, help them learn another language, it's going to take a lot more than 2 minutes. So That's something to consider. The other thing is when this is recognizing images, it can recognize thousands of images per second, which is an order of magnitude faster than any humans can recognize images. And also, if you're looking at printed characters, you're going to get much better accuracy than handwritten characters, uh, which is the case in many practical applications, whether you're scanning a document or a bill per se. Another thing that's very important is that I was able to buy a desktop with an NVIDIA graphics accelerator card for $2,500, and this actually did all that. Uh, so the economics has changed. Everybody, including myself, can now participate in machine learning and try a lot of experiments in a relatively very short time period. And there's no need to buy a desktop. You can do it on the cloud, and it's going to be cheaper and faster unless you're going to be doing it frequently. So that's another factor. Um, and What I did, illustrated was a simple CNN convolutional neural network example. Um, there's much more complex and better CNNs that were able to perform and achieve 0.23% error rates, which is really, really amazing. Finally, there are many tasks, many image recognition tasks where the computers outperform humans. And this is uh, mostly or significantly due to the fact that we have a lot more data, but also convolutional neural networks are really good at image recognition, and that's what they were built for. The comparison between kids and babies learning and computers learning is not necessarily a valid one. When kids and babies are learning to read digits or recognize text, what they're doing is they're learning to focus, they're learning what to focus on, they're learning to see, they're learning to sit up straight, they're learning to hold their head the right way. So they're learning a lot more, and they gain a lot more context and value out of it than machines learning digit recognition. Um, in addition to that, there's a lot of work involved in normalizing and labeling these data sets. It's not sufficient to have data alone. You need to have labeled data for supervised learning, and then all these images had to be normalized into 28 by 28 pixels. So that a lot of work went into it, but once you do it once, then you can reuse it again and again. You don't have, which may not be the case with humans. The other thing about kids and babies learning, maybe if adults are learning to read text from another language, you might say, hey, that's a valid comparison. Um, Accuracy, if you are trying to determine accuracy, the accuracy that I provided was for a single digit. Let's say on average the numbers are 3 to 4 digits, and for a 4 digit number the accuracy would be 0.993 to the power of 4, which is 97.2%, which means that for every 30 to 40 numbers there'll be an error. But the state of the art is 0.23%, which means that the error rate will be for every 1 in 100, or for every 1 in 200, there'll be an error, which is pretty good. Um, and if you go to text, you're going to get even better results. Uh, Actually, before I go into that, you get better results on printed letters as opposed to handwritten letters, which is mostly what you will be scanning nowadays. Um, the other thing is when you go to text, you actually get even better results, because what you can do is you can apply context. You can, add a spelling layer on top of the text, and you can do a grammar checking on top of the text. And if you combine all these methods, you'll get much better results. So that's it for this presentation. Thank you for listening and viewing the presentation. Yeah, stay tuned. There's more to come.